Hey, Calc people. This is a video on 5.3 definite integrals, and I thought I'd start off with a refresher of indefinite integrals. And you'll be able to tell the difference because, well, one, these are what we did before. If you didn't do that yet, go back and do the video and worksheet on 5.1 because you're going to be terrible at these if you don't. But quick refresher, indefinite integrals are when there's no numbers here or here. And what you do, the one trick, it's like the antiderivative is what it's called. It's the anti-version of a power rule, where you take the old thing, 4x to the third, you raise the exponent up one, so it's the opposite of derivatives where you take it down one, and then you divide by the new exponent. And usually we have simplifying to do at the end too. Hold on. All right, and then we do it to the next one. So minus, it was 2x squared, so now it's 2x to the third over 3. It's important you raise the exponent up first before dividing by the new exponent. It's the opposite of what you do in derivatives. And then 6x squared over 2. And then just remember, if you don't see an x, it's x to the 0. So when I raise it up 1, I got 5x. And here's the indefinite part. A plus c, because you don't know, if you took the derivative of this, you would land back at here, and it doesn't matter what number's at the back. If that was a 9, it would go away when you took its derivative. If it was a 25, it would go away when you took its derivative. So we just have some cleaning up to do. X to the fourth, this one doesn't really clean up, right? This one does, because 6 over 2 is 3. And it's indefinite because I'm not sure what that is. Well, now we're going to take it a notch up. Definite integrals. I like them better because there's an actual number answer. There's not this indecision of, what's that plus c? I'm not sure. Okay, definite integral looks like this, first of all. From a to b of f of x dx. So I still got the integral sign, and my dx is like my parentheses, more or less. I have my lower limit and my upper limit of integration, and I have the thing I'm taking the integral of. Okay, so let's write a little. Okay, so on here, I'll write it down for you so it's slower. So what does this thing, this definite integral, find? This finds the area of the region bounded by f of x, the x-axis, and the vertical lines x equals a and x equals b. So if I drew a picture of it, you can have any crazy graph. Like you could have a graph that goes up and then down and then up and then down and then just back up. So if I took this crazy graph f of x and I wanted to know the area under this curve between here and here, I know the other day we talked about rectangles and how back in the day they used to, they as in the mathematicians, used to have to do tons of rectangles to approximate the area under this curve with tiny rectangles and adding them up and being like really close to it and stuff like that. But what we can do with a definite integral, it's like an infinite amount of tiny rectangles, and you eventually get the exact area under a curve. So this is what it looks like when they're saying this. You're going from A to B, and you're finding the area under this curve, the accumulated area between the vertical line A, the vertical line B, the x-axis, and f of x. And I know some of you might be thinking, what happens if this graph is under the x-axis? Well, good question, you. You just have a negative area, and negative areas happen. So you have positive area if it's above, negative area if it's below. All right, so here are 5 rules for definite integration, and most of them are common sense. Just pause it and write one at a time. I haven't finished it here. So if f is defined at a, then the integral from a to a of f of x dx equals 0. And that should make sense, especially if you looked at this picture up here. If this means the area under a curve. And I say, hey, what's the area under this weird looking curve from here to here? I mean, it has no thickness, so there is no area. So it makes sense that it's 0 because you're not like capturing an area. You're just drawing a line, and a line has no area. Here's another weird one. If your integrable, which means you can take the integral on a to b, if you ever have the symbols reversed, so if instead of going from here to here, they accidentally said from way back here to way here, if they ever flip-flop these and it's not lowest number to highest number, it's an easy fix. It's not like you have to do a lot. You just do a negative version from a to b. So that's a good thing to know, because sometimes you'll get problems where the numbers are not low to high. And if you ever want to fix that, you flip-flop it. And the penalty is you have a negative sign. Okay. Remember, just pause these and copy them as you go, and then fill in the answer. All right, so here's something weird that needs a picture to go with it. But once you have a picture, this is going to be super easy. So this starts off like our normal problem. On this side, we have from a to b, the area under the curve f of x. We say the integral from a to b of f of x dx. So let's say I had this curve. Okay, I'm going from a to b. So I can say, okay, the area under this curve from a to b is the same as if I found a point C somewhere in between. It doesn't have to be in the middle. It can be close, really close to one side or the other. What that says is the area from A to C plus the area from C to B. It may have bothered you that these were out of alphabetical order, but it's kind of got to be, because you're going smaller x value to bigger x value, and then you go smaller x value to bigger x value. So basically, it's that old thing from geometry where the part plus the part equals the whole thing. That's what this is. It's kind of like the segment addition postulate, but it's more like an area addition postulate. All right, now for two easy ones that you probably would have guessed anyway. If you ever have the integral, the area under a curve of a number times f of x, you're allowed to take that number out and just find the area of f of x and multiply at the end, which is kind of handy because we're going to do a lot of that. Down here, if you ever have addition or subtraction of two separate functions in an integral, you're allowed to break those apart to just do f of x and then add or subtract the integral of g of x from a to b. Okay, so now let's do some examples, because we haven't actually gotten to the whole kit and caboodle, the point of this thing, and I'll show you on the next page after we got the rules. Okay, so here's an example to test if you got what you were supposed to get out of those rules. First of all, we're given three things. Normally you aren't given this, and we'll start actually solving these soon with our tricks. But this is just a get if you grasped all those rules from before. I'm giving you that I already know the area under the curve from 0 to 5 is 10. The area under the curve from 5 to 7 is 3. The area under the curve from 3 to 5 is 4 units. So if you were asked, what's the area under the curve from 0 to 7, you're like, oh, well, I got 0 to 5 here, and I got 5 to 7 here. So if I can picture that graph where I'm adding the part plus the part, this is basically asking the whole. Or it's seeing if you understand that rule with the part plus the part equals the whole. So 13 is going to be your total area from 0 to 7. This one's checking something else. You're going from 5 to 0, which is a lot like 0 to 5, but it's just backwards. Remember the penalty if you had them backwards? You just put a negative version of the area. Okay, how about from 5 to 5? That's a rule that's like you're picturing area under the curve. There is no thickness to it, so there is no area. Therefore, the area is 0. 0 to 3. Now this takes a little more work. This is like you go 0 to 5. There's the whole thing. And from 3 to 5, you have the part you don't want, so you have to remove it from the whole. If I drew a picture, and you can always draw pictures, random thing. Here's from 0 to 5. You have an area of 10, right? Imagine that area. And then from 3 to 5, you have an area of 4. So it's basically 0 to 3 is the part you care about, and it's just 10 minus 4 is 6. So it's good to get a visual in your head of all these. This one's a little different because now I got it backwards, and hopefully you notice that negative 5 there. So I flip-flop it. I don't have to do this work again, right? Because I already know the answer from 0 to 3 is 6. So if I flip-flop, it's a negative 6. But I have a number in front of it, so I have to do negative 5 times negative 6, which is regular 30. All right, so those are just testing the rules. Let's learn the trick of the day. All right, so if we take a look at your homework worksheet for 5.3, I'm going to look at this problem here, and I want to show you two different ways to do the problem. The second way is the way we're going to do it more often. Actually, let me show you the first way while we're here. So the integral from 2 to 7 of 3 dx. Okay, so we're going to do this one. So the integral from 2 to 7 of 3 dx. Now this is a problem back in the ancient Greek kind of time. They could do this because if you actually graphed it, remember this is y equals 3. It's your y value. It's your f of x. So if I graph that, that just looks like this, right? 1, 2, 3. I draw a horizontal line here. That's the graph of f of x. And then I don't want the whole area underneath. I just want from 2 to 7. 1, 2, 3, 4, 5, 6, 7. And right? Do you know the area of this shape? I hope so. Because you can just do, okay, the base is 5, the height is 3, so I can do the area equals 3 times 5, area equals 15. So the integral must be 15. Okay? So that's the old way. The new way is even cooler, and that is to use this new integral trick, the antiderivative thing. So remember what you would do if you didn't have any numbers there, right? If you didn't have any numbers, what would the antiderivative be? It would be 3x, and then you'd put plus c. Except this time, if there are numbers, we have more work to do. And this is our rule. You write the antiderivative in a box, and at the bottom you put a 2, and at the top you put a 7. And this actually splits into two problems. You'll do the first one with 3x and the 7 plugged in, and then you'll do the second one with the 3x but a 2 plugged in. And guess what? 3 times 7, oops, not plus, minus, oh geez, minus 3 times 2 equals. Basically, what we're doing, it's crazy that this formula works. I'll give you the full formula on the next quick video and a couple more examples. What you're actually doing is, if I drew a picture of it, right, remember that picture? You're finding, when you plug this in, why you do this, you're finding the area from 0 to 7, right? That's what this one is, 21, because it's a rectangle that's 7 by 3. And you're taking off the chunk you don't want, right? Imagine removing this chunk. How much is that chunk? It's a 2 by 3. 2 by 3 is 6. So it's like you're taking the whole area back to the y-axis and removing the part you don't want. That's what every one of these problems is. And we'll write up the thing more formally, so get to the next video. I'll write the real formula and then do a couple examples to help you out for your homework.